Xin kính chào quý phụ huynh và các em học sinh thân mến. Chào mừng đến với trung tâm IB and A-Level Learning Center và tôi là thầy Tài. Trong video này tôi sẽ giải thích cách giải một bài toán về Conservation Momentum trong đề thi AP Physics 1 năm 2026 vào tháng 5 vừa rồi. Câu hỏi số 2. Two small disks R and S are on the straight horizontal track. At time t equals 0, disk R of mass m0 is located at the position x0. Disk R is initially moving with speed v0 in the positive x direction. Disk S of mass 3m0 is initially at rest, as shown in the top view in figure 1. Frictional forces are negligible. At t equals t1, the disk collide. Immediately after the collision, disk R moves with the speed 1/2 v0 in the negative x direction. As we have the figure here. Okay, mình sẽ tóm tắt một số thông tin của bài này nhé. Let's summarize. Before the collision, we have the mass of the disk R. Let's write the R here. The mass is m0, the speed is v0. And then after the collision, one more thing. The S disk on the right here, This is v0 to the right, so let's write it a positive value. And we take the positive x direction to the right, to the right like this. The mass of the disk S is 3m0, and the initial speed before the collision, or more accurately, the velocity is 0. It was stationary. And then after the collision, of course, the mass is still the same, m0. The velocity of the disk R after the collision is negative 1/2 v0. It bounces back to the left. Okay, it does not move continuously to the right in the same direction, but bounces back. This is the most important thing in this question. If we forgot to identify the direction of this velocity, then every step later will be incorrect. For the disk S, of course, the mass the same, 3m0, and we need to find the speed, the velocity of the disk S later using the conservation of momentum suddenly, because for all the types of collision, including elastic and inelastic collision, the total momentum of the system, which involves the two disks, is always conserved. One more thing, we have negligible friction. So it is a confirmation, given information that allow us to know for certain that the total momentum of the system is conserved. Okay, because negligible friction means that the external force which create a negative work, reducing the momentum of the system, reducing the kinetic energy of the system, is negligible. Okay. Part A of this question. The momentum vector diagram in figure 2 represents the momentums of disk R and disk S before the collision. Okay, so we have the disk R here, the vector which represents the momentum is to the right, and its length is 4 spaces, grid spaces. We can call it 4 small squares, just square, but 4 grid spaces is the point. And the disk S has no vector because it was stationary, standing still. Okay. Now, part A. Draw arrows on the figure 3 to represent the momentum vectors of disk R and disk S after the collision. Each arrow must start on and point away from each dot. If the momentum of either disk is 0, write P equals 0 next to the dot. Draw the length of each arrow to represent the magnitude of each momentum consistent with the scale used in figure 2. Mình cần phải vẽ nó với cùng một cái scale ha. This is a very important information with the same scale. So initially the disk R has the momentum of 4 grid spaces, but after the collision the velocity is negative 1/2. Let me write here after collision V of the disk R is negative 1/2 v0 in the opposite direction to the left. Okay, therefore the momentum, which is mass time velocity, is also in the opposite direction, which is to the left also, and its length is 2 grid spaces. Of course, this is my note notation to remind you you do not need to write with text, just draw with arrow, and you can use the notation PR final like this to indicate the momentum. Remember, the length of this arrow must be exactly 2 grid spaces like this, which is proportional to the magnitude of the momentum of the disk R, which is m0 times negative 1/2 v0. Okay, and the vector which represent the momentum of the disk S here, we need to find it by using the conservation of momentum. Okay, P before the collision, Pi equal P final after the collision. Before collision, the disk R momentum is m0 v0, and the momentum of the disk S is 0 because its initial velocity is 0 here. Okay, after the collision, m0 for the disk R negative, let me put a multiplication symbol here, negative 1/2 v0. Okay, and then we add the mass of the disk S, which is 3m0, and the velocity of S final. We need to find it. Okay, we can now simplify the mass m0 on all the terms in this equation because every term contains the m0. Okay, so we have just v0 on the left hand side equal negative 1/2 v0, oops, v0 here, and 3 times of vs final. Okay, so from this equation, derivation, begin your derivation writing. Sorry, let me move my writing the equation here downward. You need a space, very little space here that allows you to write a solution, but you have to use that space anyway, because we do not have additional empty space to write it. Okay, anyway, from this equation, we can derive the final velocity of S, which is v0 plus 1/2 v0, and then we divide the total, number 3 here, number 3. This is 1 and 1/2, which means 3/2, and then divided by 3, we simplify and we get only the number, sorry, 3/2/3, 1/2, 1/2 v0, and it is positive, which means the disk velocity of the disk S is to the right. Okay, to the right in the positive direction there. So 1/2 v0, momentum of the disk S, we need to write the momentum. Draw the vector which represent the momentum. Momentum of the disk S after the collision is the mass 3m0 multiplied with this speed, which is 1/2 v0, like the same magnitude, the same speed, 1/2 v0, but to the right, not to the left, like the disk R. Okay, so we have 3/2 m0 v0, 3/2. The initial momentum of the disk R, let me write here, initial momentum of this R, initial, is m0 v0, which means the final momentum of the disk S here is 1.5 times greater than the initial momentum, 1.5 times. I'm emphasizing on it. Okay, so the initial momentum of this disk R is 4 grid spaces. This one 1.5 times, so 4 times 1.5, we get 6 grid spaces is our answer. So this vector, we need to draw it with 1, 2, 3, 4, 5, 6. Okay, 6 grid spaces like this. This is the P final of the disk S. One more thing is that when you take the sum of these two vectors, the red vector here and the violet vector here, let me draw that with the black diagram, black color. This vector, which is the final velocity of R, and when you add it with the violet vector, which is the final velocity of the disk S, the sum is a vector like this, which is identical with the initial momentum before the collision. Initial, okay? So that's the point. One vector which is 2 grid spaces to the left, the other vector which is 6 grid spaces to the right. When you add them, you get the sum, the total is 4 grid spaces to the right, which equal to the initial momentum. That's the point. Okay. So I forgot to do one more thing, to calculate the kinetic energy of this this S immediately after the collision. So we got here the final speed of this S, which is 1/2 v0. To calculate its kinetic energy, let's write Ke of S after collision. Final. Just use the formula 1/2 mv squared. The mass is 3m0 and the speed is this thing 1/2 v0. We square it and we get the answer. 1/4 3. We have 1/4 times 1/2 is mean 8 at the bottom. Okay, 3/8 m0 v0 final square v0 square. So this is the answer, kinetic energy of this S after collision. Okay. Now let's continue. Part C. Graph shown in figure 4 represent the positions of S as a function of time t from t equals 0 until t equals 1 t1. Figure 4. Let's look at that figure 4 below. T from t equals 0 to t1 for the two disks and the center of mass of the system. On the graph on the figure 4, draw 3 lines that represent the positions x of the disk R, this S, and the center of mass of the two disk system as a function of time from t equal t1 to t equal to 2t1. Distinctly label each line. Okay, let's observe this diagram. This graph, we have 3 lines. Okay, the disks R here, the solid black line. You can see that the gradient of this disk is 2 because the increase in position is 4 grid spaces. Okay, let me draw that. This increase is 4 grid spaces, and run, which is the time interval from t to t1, is 2 grid spaces. So we have the gradient of this graph is 4/2, which is 2. Okay. The important thing when you look at one graph is the meaning of the quantities on the two axes. X here is position or displacement, okay, and t is time. Therefore, the gradient of this graph, position visit time, means velocity. We have a positive gradient, an upward line like this, which means the velocity is positive. And if we have a downward line which has a negative gradient, it means the velocity is negative. Okay. This line represents the velocity of the disk R moving before the collision. Okay, and the disk S was initially stationary, so it's horizontal like this. And then we have the dashed line, which represents the center of mass. I would like to remind you the very important formula that most students forgets about the center of mass. That equation is the velocity of the center of mass CMO, is the total momentum P1 of the first object plus P2 of the second object before or after collision, doesn't matter, at any instant, but the point is the sum, the total momentum, okay, divided by the total mass of the two objects or many objects if the system involves more than 2 objects, m1 plus m2 total mass. Okay, before the collision we have the momentum P1 is m0 v0 and the momentum of the second object is 0, and the total mass is m0 plus 3m0, which is 4m0. So the velocity of the center of mass is 1/4 v0, 1/4. Okay, so see that this dash line, it has 1/4 gradient, the rise is 1 and the run is 2, so the slope, which is the velocity of the center of mass, is 1/2, which you see is 1/4 of the gradient 2 here of the velocity of the first object, that is R. Okay, so the graph is certainly consistent with the given information of the question. Now we need to draw the 3 lines which represent the velocity of this after the collision and the center of mass. Okay, the most important thing of this type of question is that the meaning of the gradient is velocity. Okay, just focus on this idea, this knowledge, and you can solve this problem easily. After the collision, the disk R here has the final velocity after collision, which is negative 1/2 v0, bouncing backward to the left. Therefore, its velocity is negative, which is represented by a downward line. Okay, downward line, and its gradient is 1/2 of the original gradient. This is the original gradient, which is 2. Okay, now 1/2 of 2 means the gradient is 1, which means when the time is 2 grid spaces, the run, which is the rise, which is now negative, is also 2 grid spaces, which means it goes from here to this point. 2 grid spaces to the left and to the right, and 2 grid spaces downward. Okay, which means the gradient is 1/2 of this original gradient. Okay, let's draw that line. This is the line which represents the velocity of the disk R after. So how should we label that? Okay, let's do the label, huh? V R final. Okay. Now this S we have just identified earlier up here. The velocity is 1/2 v0, which means the gradient, the slope, is also 1/2 of the original slope of v0. V0 has the slope of 2 here. Okay, so now the slope is 1, which means let me use the different color. This one, huh? The black color. The gradient is now 1, which means the run is 2 and the right is also 2. This is grid space. We draw a line going up here, huh? There. So this is the V final of S final there. So you see that they have the same magnitude, the same speed, but different direction. One disk goes to the left and the other disk goes to the right. Okay. So here are the two lines to grab up the two disks. Now the last thing, the line which represents center of mass, it has the same gradient because the total momentum P1 plus P2 here is conserved constant. So the velocity of the center of mass is also conserved as well. Okay, which mean it had the same gradient. The line keep going, in a straight line like this. Okay, going straight, which means we draw a line over here. So that center of mass, draw a dash line. This is the V of the center of mass, the 3 line. Wow, we finished this question. Okay, conserve, that's the point. Rồi, bây giờ thầy nói thêm một xíu nữa về cái center of mass nha, cái kiến thức về center of mass này. Ở trên này thầy có một cái bức hình, ví dụ là một cái người ngồi trên thuyền. Và ổng cầm một quả bóng, nó hơi nặng một tí nha, ngồi trên thuyền, trên mặt nước yên tĩnh đó. Và sau đó thì ông này sẽ ném quả bóng đó nó bay và nó rơi vào cái đầu bên kia của chiếc thuyền. Ở trên hai cái hình này thầy đã chọn cho nó cùng một kích thước, một cái scale. Ok, và đánh dấu vị trí này. Ban đầu cái vertical line này đi qua cái phao nổi ở chỗ này, nó nằm ở chỗ này của cái thuyền. Sau đó thì khi mà ông này ông ném cái quả bóng đó, có lẽ là mình nên xem một video đi ha. Rồi, somewhere. Khi ông ném quả bóng đó thì chiếc thuyền nó sẽ tự động nó bị di chuyển ngược về phía quả bóng bay. Quả bóng bay về bên trái thì chiếc thuyền nó sẽ move về bên phải. Đó là conservation of momentum. Quả bóng có momentum sang trái, chiếc thuyền và người sẽ có momentum sang phải để cho total momentum không thay đổi ha. Cho nên là khi mà chiếc thuyền khi mà quả bóng nó rơi vào đầu bên kia của thuyền thì cái thuyền và người này, system này đã move một đoạn. Tuy nhiên cái điều quan trọng là cái center of mass nó sẽ không thay đổi vị trí ha. Tại vì là cái total momentum là 0 ban đầu trước khi mà người này ném quả bóng thì toàn bộ momentum của system là 0 ha. Ví dụ như center of mass nó nằm ở chỗ này. Đó, nó cách cái đoạn này là ví dụ như là 2 cm chẳng hạn thế. Thầy đang vẽ trên hình thôi nhé. thì sau khi ném quả bóng nó rơi xuống ở chỗ nào đó thì cái center of mass của system đó nó vẫn sẽ là cái vị trí cũ ở trên ở trên trên mặt đất này, trên cái coordinate system reference frame này, tức là center of mass bây giờ nó sẽ nằm ở chỗ này này, chứ nó không phải là chỗ này đâu ha, nó không phải là chỗ cũ này đâu, nó sẽ là chỗ mới này. Nhưng mà vấn đề là vị trí là so với mọi vật ở xung quanh, so với quả đất của mình, reference frame, thì vị trí center of mass nó sẽ không di chuyển, nó stationary, tại vì velocity của center of mass là constant, là zero. Ok. Rồi, mình tiếp cái câu cuối cùng nha, part D. Câu này nó hơi khó nha, mình phải chú ý cái direction nó đi xuống ấy. Part D. During the collision, the magnitudes of changes in momentum of the this R and this S are absolute delta PR and absolute delta PS, respectively. Indicate whether delta PR is greater than, less than, or equal to delta PS by writing one of the following. And briefly justify your response by referring to the fundamental physics principle. Okay. Cách đơn giản nhất để làm bài này, we write the change of momentum of the two systems. For the disk R, the change momentum is, let's write delta PR, is the final momentum, which is negative m. Thực ra mình có thể viết m trước và velocity. m0 times negative 1/2 v0 minus the initial momentum, which is m0 v0. So suddenly we have negative 3/2 m0 v0. And the absolute of this PR, change momentum, which means like the magnitude, or we can say the modulus of the change in momentum of this R is, absolute of this negative number is positive 3/2 m0 v0. Okay. Similarly for this S, sorry, let me move everything to the left and reduce the size so that I have more space to write the solution. For this S, we have delta PS, the final momentum is 3/2. 3m is the mass, and the velocity is 1/2 v0, and initial momentum is 0. It was stationary. Okay, so this is 3/2 m0 v0, and therefore we can see easily that PS magnitude is 3/2 m0 v0, which is exactly the same with the change momentum of this R. Therefore, we write the conclusion. The conclusion is the magnitude of the change momentum of R and the change momentum of S is the same, suddenly, which is this option. But we need to write it down, not just circling the answer. Okay, and then we write explanation, justification in the fundamental physics principle. Okay, we can write it as follow: because the conservation of momentum of the system is always conserved, the total momentum is always conserved, I mean of the system. So the change in momentum of one object, which is the disk R, which is the change momentum to the left direction, okay, is the same but opposite, so that the total change is 0, opposite, okay, to that of S, so that the total change in momentum, total change is 0, which means momentum does not change, momentum is constant, conserved. Okay, we see the explanation and we finish the part D of the question. Yeah, the change momentum of the disk R to the left, the change momentum of this S to the right with the same magnitude cancel out. Total change is 0, no change at all. Okay. Trong bài này thì mình không cần quan tâm là cái conservation này là cái collision này là elastic hay là inelastic. Tại vì đề bài này thì tại vì là người ta không hỏi cái câu nó là elastic hay là inelastic. Hình như là có một cái câu về kinetic energy mà thầy quên làm ha. Ok. Cho nên là mình không cần phải identify nó elastic hay không. Nhưng mà nếu muốn identify thì mình sẽ tính cái kinetic energy before and after collision và compare nó với nhau ha. Hoặc là có một cách khác đơn giản hơn như sau. đó là mình sẽ để xíu tìm cái trang trống. Mình sẽ tính cái change in velocity, gọi là relative velocity of approach, relative velocity or speed, relative speed of approach. Và mình check thử xem nó có bằng hay là giống với lại là relative speed of separation ha. Of separation. Relative speed of approach là u2 minus u1. Nó là lúc sau nó là negative 1 half v0 ấy, và v1 nó là v0 ha. Thì cái change này nó sẽ là negative 3 over 2 của v0. Còn relative speed of separation thì nó ngược lại nha. Nó không phải là u2 minus u1 mà là v1 minus v2. Tức là v1 là của s này, là ban đầu là 0 này, 0 trừ đi cho 1/2 của v0 thì nó bằng negative 1 half v0. Như vậy thì có nghĩa là nó khác nhau, hai cái này nó khác nhau. Thì cái collision này nó không phải là elastic mà nó là inelastic ha. Elastic collision. Cái này thầy nói thêm cho mình biết thôi chứ không cần phải quan tâm lắm đối với bài này ha. Thank you very much for spending time and watch this video. If you have any questions, just please let me know in the comment section, please. Thank you.